So yes, I'm currently at the IAS in Princeton, and I have the great fortune and honor to work in Einstein's office, former office. It's an inspiration, and the person that is one of the, let's say, one of the scientists that is a big inspiration for me is Neumann, John von Neumann, who was working next door to this office. And so what I admire about him is that he was, on the one hand, he was able to take a very complicated scientific situation, scientific question, and simplify it. And not only simplify it in his head, but able to write it down and explain it to people in the simplest possible terms when you just read it and think, oh, that's actually a very, very clear picture. He was also not, he was not very picky about the problems that he was working on. It was not, he was at the IAS, and just before he was working on the what is now known the Gödel incompleteness, a very abstract, high-level mathematical question, and when he realized that Gödel actually beat him in proving the full incompleteness theorems, he first of all he supported Gödel very much throughout the rest of Gödel's career, and he turned to an applied problem, how to implement Gödel's formalism in a computer. And he had to actually argue with the people at the IAS, which was considered to be the ivory tower of high-level abstract science, especially mathematics, very far from applications. He had to argue with them to be able to, secure funding and a place to build a computer. One of the first electronic computers. So there was no problem that was beneath him. If it was an interesting problem, he would work on it, and I think that's very inspiring. Yeah, beauty and mathematics, that's an interesting and very wide topic, and Einstein was certainly very poetic about what he thought true scientists are or are supposed to be. He was talking about the temple of science, which is populated by 3 types of scientists, roughly speaking. The first one are the people who are very good at it, who do it out of being able to be very efficient and very good and make results, like kind of sport. Then there are those who do it motivated by a sort of application point of view, a utilitarian point of view. We have to prove this result, or we have to work out this problem because it has certain applications. And then he talks about the third type of scientist, which he compares to artists, like painters, composers, and poets, who do it out of a kind of inner drive. And I think I would say that probably each type of scientist is present in all of us. At some moment, we do mathematics because we can. Most people in high school and even at university would study mathematics because they're actually quite good at it. They take part in we take part in competitions. We get some sort of satisfaction about being able to get good grades. Let's say it's something that we enjoy doing. And then comes a moment later when we think of, let's say, more established scientists thinking of grant applications, something that, what kind of problem should I work on? It should be something that's useful to the scientific community, that's useful for my particular field, or useful for mathematics in general, or it has some application in physics or biology or other subjects. So there is this kind of utilitarian aspect. And ultimately, especially when you reach a stage beyond the publish and perish publish or perish pressure, that you have to think about what kind of problems you want to work on. There is a sort of inner motivation. Which problem do I consider interesting? Do I want to work on a problem because I know how to do it, I have the method, so I can just write another paper? Or do I want to work on it because my colleagues in fluid dynamics told me this is an interesting question? Or do I want to work on it because I think it's a nice problem? It's an interesting question. It's something that just kind of caught my attention, and I just want to solve it. So it's a matter of taste, and this is, I would say, this is the artistic part that is probably present in all of us. So my field of mathematics is broadly speaking, partial differential equations. And in the past years, I've been working on fluid dynamics, the continuum equations describing the motion of fluids, such as the Euler equations or the Navier-Stokes equations. And in particular, I've been interested in the question of, how to describe turbulent solutions. Turbulence is a ubiquitous phenomenon, and somehow it's a question how these simple equations, which just describe the basic law, Newton laws of conservation of mass and momentum, how they are able to describe this sort of very complex dynamics, this very complex motion that happens on many different scales that we observe in turbulent flows. And what is interesting is that this sort of complex behavior that arises from a simple set of equations, this has a connection to a phenomena in geometry that was essentially discovered by the work of Nash and then later Gromov. What is called H principle, something that amounts to saying that certain problems, which can be described by partial differential equations, have many solutions. There's a large level of flexibility, and in the case of turbulent fluids, this flexibility is present at the very small scales. So this is what the topic that I've been working on in the past years. I think that the greatest challenge that one faces, especially after university, the first time it happened to me, at least, was during the PhD, and then later it happened as a postdoc on several occasions, is to cope with periods, time periods, where you're not making any progress. It's a psychological thing. I think that looking back at how I was progressing in my research output, these periods were not so bad. But when you're in one of these periods and you don't know how long they're going to last, and you see, let's say, your colleagues or your friends making progress, there are certain breakthroughs happening close to your field, and or you might think, other people are going to solve the problem you're working on. That is that's a difficult thing to cope with. That's a challenge. But to overcome these periods, to have the faith that you're going to be able to make progress, maybe not on that particular problem, but try to think of a different aspect of the problem or a different problem, that's or just try to do something completely different for a while to get your head clear. So you have to take a step back. And but this is a challenge, to be able to breathe in, breathe out, take a step back. And so receiving these prizes is of course, it's very nice. It's a great honor, and also a great relief for my career that it is being appreciated. But the moments when I have a feeling of achievement is not when I'm receiving the prize or when I hear about it, but the moment when I'm able to nail down the theorem. nail down the proof. That's the real feeling of success. You know, it's like you know, that's it. I've got it. And sometimes, especially if I've been working on it for a long time, that's a feeling that is difficult to describe. I think it's so that was certainly the case when with my colleague Camilo de Lellis, we were finally able to nail down how to construct continuous solutions of the Euler equations. That's probably the moment when I had the greatest feeling of achievement. So that's a challenging question. What is my scientific perspective as a new director of the Max Planck Institute in Leipzig? It's a question that has been that I've been thinking about a lot, especially here at the IAS. I was reading the history of the IAS, and one of the main questions that people had to answer is, what does the institute stand for? What is it that people working at the institute should be working on? And even though the founders and the first director had a pretty clear idea, it changed. People like Neumann or Hermann Weyl, Veblen, they had their own ideas of what research they want to work on, and that's the direction that the institute moved on. So the question in Leipzig is what is in this name, mathematics in the sciences? Is it an institute that is working on mathematical or applied mathematical problems? But then what does it mean, applied? Is it something that you work on mathematical problems motivated by questions in the applied sciences? Or is it an institute where you work on problems which are supposed to help the applied sciences? And I would certainly both. And I think that what is certainly an aspect in terms of the relationship with the more applied sciences is that the Max Planck Institute is part of a huge network of research institutes, most of which, at least the ones I know, are in the applied sciences, at least in the section where the Mathematics Institute is in. And I'm certainly looking forward to working with the other institutes, working with the people in the other institutes. There's in fluid dynamics, in turbulence, in astrophysics, in meteorology. There are a number of institutes where people are working on problems that I've encountered from a very pure side, and even just to talk to them, to understand what is it that they are interested in, what is it that they're working on, and how do they think about these problems? How do they, so to give another example, I rarely work on numerics. I did some numerics for my PhD, but I haven't really been doing numerical simulations. But when I speak now to people working on large-scale numerical simulations in fluid dynamics, it's not just a question of you know, just implementing some of the theory. They have to think about how to do that. It's sort of what Neumann was doing when he was building the computer. He had to speak to the engineers. How are you going to arrange these vacuum tubes so you get something that is the precursor of random access memory? He had to actually solve bare hands problems, like, you know, how to build this thing. And people working on numerical implementation have to work on, you know, certain issues when you make approximations, when you pass from the Fourier side to the real side. How do you multiply two functions? Where do you introduce errors? Where is the numerical precision the most important? These are all interesting problems that they have to solve, and so I'm definitely looking forward to these discussions. This is also related to the scientific perspective. I've been involved with. So I think one topic that is hasn't been explored too much, but that I think should be explored more is the interaction of discrete mathematics and continuous mathematics for analysis on the one side, and let's say combinatorics, graph theory, and so the interaction. There's certain problems that so the natural interaction or place where these two fields interact is when you take limits, large-scale networks, or limits of large graphs, and on the other hand, when you think of continuous objects like a PDE, it's sometimes very useful to look for discrete approximations. And then the question is, how do you, which kind of property should a discrete approximation preserve from the partial differential equation? Which symmetries should it preserve? Which conserved quantities? So these are kind of interactions, and then that might lead to going from the continuous to the discrete, might lead to new insight of what happens actually at the discrete level. And when you go from the discrete to the continuous, you might get some simplification of the complexities that, let's say, these large discrete structures have. And I've been involved in many discussions now with a group of mathematicians in Hungary, and I'm hoping to establish a more institutional connection between the Max Planck Institute in Leipzig and the Rényi Institute in Budapest, which is, I would say, one of the leading centers in the world in discrete mathematics. So I guess I'm in a unique position here in that, first of all, I know the Max Planck Institute from more or less all possible career stages. I was a PhD student at this institute. I was at some time a postdoc, and then an external member, and now I'm a director. And on the other hand, I know the university very well because, as a PhD student, you have to face the regulations, Promotionsausschuss, and so on of the university. And I've been a professor at the university for the past 11 years. So I have a sort of different level of understanding of where the relationship is very fruitful, where there's potential for improvement, and where one has to be a little bit careful about or where one could improve the relationship, or have an understanding also of where there were difficulties in previous times. The Max Planck Institute for Mathematics in Leipzig has a different history than the one in Bonn, and in that it didn't really grow out of the mathematics at the university, even though there was a strong connection, obviously, with the founding director Zeidler. But the other directors in the past have not been coming through the university. And so there is a sort of tension arising from this, which I think should be turned into a kind of positive tension. It's a potential that one could explore more. And it has been explored in terms of joint hirings, a joint PhD program, hirings at the professor level, at the postdoc level, and so this is something that has been very fruitful, and I'm very much hoping that I will be able to build on this close cooperation that has existed so far, and and hope that this interaction and this cooperation will go to new levels. My advice to young mathematicians would be, well, first of all, there are no stupid questions. Every question that you ask is a meaningful question, and you should not think that, oh, this question is probably something I should know the answer to, so I don't dare to ask it. So that's the wrong way to go about. You have to start a conversation with your colleagues, other PhD students, with postdocs, with your advisor or other professors, and the best way to start a conversation is to ask questions. And I've been at the stage where I didn't dare to ask certain questions because I thought, well, I should just read the book and then I should know the answer. But of course, reading a whole book, it takes much longer than just asking a question and getting a fast answer. And so you should keep that in mind. It's always good to ask questions. Also, for let's say for your advisor to be able to understand where is your level of understanding. What is it that you're wondering about? Where are you currently heading to? Where can the advisor help? And also in general, just to keep wondering. There is no, you should not get stuck in one particular problem or one particular aspect of a certain theory. You should try to keep an open mind all the time, even if it's about topics which are pretty far from your own subject. So the millennium problem that's closest to me is the Navier-Stokes problem. The question is, you have the Navier-Stokes equations in 3 dimensions. So they just described basic Newtonian laws applied to a continuum, applied to a fluid, which is incompressible. And the question is whether a finite time singularity, in finite time, a singularity can arise from smooth initial data. So it seems like a pretty... So what is interesting is that it's a very specific question that one could ask, this question of finite time blow-up, one could ask about many other PDEs. For instance, one could ask it about the Euler equations, which seems even simpler, and I would say the Euler question would be even more interesting. But the Navier-Stokes question is nice because it's a sort of base example for a general type of phenomenon where we need to come up with a new theory. So it belongs to a large class of partial differential equations, which people call supercritical, which means just in terms of scaling, when you scale the equation or you zoom into a solution, you see something that could, in principle, in terms of exchange of energy, could lead to blow up. It could happen that in finite time, energy starts to concentrate on smaller and smaller regions until, at a certain finite time, the energy becomes the solution becomes infinite at a point. That could, in principle, happen. However, I guess most of the instances that we know where blow-up does happen in a PDE are based on one-dimensional models, where due to some sort of symmetry considerations or invariances, we are able to reduce the problem to a very specific ODE. And for ODEs, we know how to classify them in terms of the global existence of blow-up. We can calculate the solution. And the Navier-Stokes equation doesn't seem to have anything like that. So it means that this simple reduction to one dimension doesn't work, and we need to come up with a completely new idea of how to try to work genuinely in 3 dimensions and deduce something about the dynamics of the equation, something that becomes kind of self reproducing, and that where the energy is concentrating on smaller and smaller regions. And so that I think, even though it's a specific, it would be strange that, you know, there is a question, a millennium problem, where you just pick one equation, and we're asking about blow up for that particular equation. But the I think what makes the problem interesting is that it's I mean, the hope is that if we are able to show blow up, or show that there's no blow up, it would give us intuition about other equations of a similar type. So I'm here in Einstein's office this year, and this is a big office. It's more like a living room, and I've been playing chamber music. I don't know, maybe Einstein has also played chamber music in this office. So I play violin, and in particular string quartets or trios or all kind of arrangements is something that's a big passion for me. It's a way. It's actually interesting that wherever you go, you always find other mathematicians or other scientists who also have the same passion. Oberwolfach is a great example. There's a fantastic music room with all the sheet music, with the piano, with other instruments. So usually there is a group of people which finds itself, and we can play some chamber music. And it's the same here at in Princeton. There are many very good musicians, other mathematicians, physicists, and so this is it switches off the analytical mind and enhances the what Einstein might call the poetry part of our mind.